First, I'm going to draw acetyl-CoA in green here since we already radio-labeled its carbon as green. And then we'll put acetyl-CoA right next to it in red with its radio-labeled carbons highlighted in yellow so we can distinguish between the two throughout this process. Keep in mind this is enzymatically catalyzed. So this basic amino acid residue is going to come in and it's going to steal a proton off of this alpha carbon from the acetyl-CoA. When it steals that proton off the alpha carbon, the electrons that were holding that proton to this alpha carbon are going to jump to be shared between these two carbons. At that point, our carbonyl double bond will go ahead and transfer its electron density onto the carbonyl oxygen. Notice we haven't touched our acetyl-CoA yet. So at this point, we have this really electron dense double bond between these two carbons, and that is going to go over and it's going to attack the carbonyl carbon on our acetyl-CoA right here. And that is going to cause these electrons to jump up to this carbonyl oxygen. At the same time, keep in mind that our carbonyl double bond is reformed when that electron density jumps over and attacks the acetyl-CoA. So what's happened here is we've still got our CoA attached, and now we have reformed our carbonyl bond, and here is our radio-labeled carbon. I'm going to go ahead and radio-label that here. There's the green. All right. And now we've formed this new bond. Now that is bound to this carbonyl carbon right there. And so here is going to be that radio-labeled methyl group, right? It's just moved up a little bit, right? Because we're forming a tetrahedral intermediate from what was a trigonoplanar carbonyl there. And now our carbonyl oxygen just has a single bond to it, and it's holding this electron density that had jumped up to it from the carbonyl. Keep in mind, we're tracking all of these radio-labeled carbons still. All right, so at this point, the last thing that we have to do in order to complete our reaction, in order to get our HMG-CoA, right, because that's where we're headed, is we need to react this thing with H2O. This oxygen, right, that has this negative charge, is going to go ahead and pick up that proton off the H2O, okay? Then that meaning that these electrons here between this bond just jump onto the OH. So we're going to scroll down a little bit here and demonstrate how this molecule looks once that oxygen has been protonated. And notice that the hydroxide from which we took the proton is still hanging out here. So that is going to come in and perform a nucleophilic attack on the carbonyl carbon of the original acetyl-CoA, this green one over here on the left. So when it performs that nucleophilic attack, the CoA group here is going to be our leaving group because the sulfur attaching it to the carbonyl carbon is such a large atom that it's able to delocalize that negative charge over a large atomic radius, making it much more stable than your typical monoatomic anion. Okay, so then what we end up with here at the end of all of it is this molecule. Moving from left to right, we've got our OH that just came in, and that's attached to the carbonyl carbon of our original acetyl-CoA here in green, and that goes down and is again attached to the just CH2 that was part of the original methyl group from the original acetyl-CoA again. And this is where we connect our original acetyl-CoA with the initial acetyl-CoA, the thing that started out in red. Everything here is in red, right? And these two connect on the original left side carbonyl carbon of the acetyl-CoA so that we have this methyl group that was initially labeled, as well as the initial carbonyl oxygen, which is now a hydroxyl group having been protonated by the water that we brought in. And finally, we throw in the original acetyl-CoA, which hasn't been touched. So what we've done here is enable ourselves to easily identify all of the initial radio-labeled carbons that were mentioned in the passage, which is going to turn out to be paramount to answering at least one of the questions on this particular passage, as well as understanding fatty acid synthesis and cholesterol synthesis, both of which are definitely going to be tested on the MCAT. That wraps up the topic for this video, which was just going through this particular synthesis reaction. However, if you would like to understand why we were covering this reaction in the context of its overall passage, you can check out part 1 of this series, or if you've already seen part 1 and would prefer to go ahead and move forward with answering the questions for this passage, you can check out part 3 coming up next. And for more clear, concise explanations that you won't find in any textbooks, check out some of our other videos or come pay us a visit at onesourcemedicine.com.